Okay, well, now that we have the tools to describe physical reality, namely three-dimensional coordinates as well as scalars and vectors, it's time to tackle physical reality, and in this presentation we will talk about the work that is done by a force that stands at an angle to the distance at which the object moves. You'll rightly say that that's physics and this is a math class. However, the reason why mathematics will always remain so relevant is because it is the tool to describe physical reality. So in this course, especially in the multivariable part of this calculus course, we will use physical phenomena as much as possible to describe and motivate the mathematical concepts that we are introducing. This particular one actually goes back to something that you may have also had in childhood. Let's take a look at our first example here. So we're looking at work when force and distance are at an angle. And so think back to sometime in your childhood, you may have had a pull toy. A toy kitten was something that I remember that my children had. And well, what's a pull toy? It's basically a mass. Okay, the toy kitten was not a rectangle, but it's basically a mass that is on wheels, and it can move along the presumably horizontal ground. However, the string that is attached to the pull toy is typically not pulled horizontally, because typically you would hope that your children are taller than their pull toy, because otherwise you'd either have a dangerous pull toy or a very small child. Okay, so the force that is being exerted through the string on the pull toy is not parallel to the distance that the pull toy is traveling. And so the question therefore then is, how does our definition of work equals force times distance change? And indeed, we ultimately want to come up with a definition for a scalar product that will not force us to change the definition of work equals force times distance. However, what happens is, what physicists have verified, is that when force and distance are at an angle theta, then if you project the force vertically down onto the distance, you get a component of the force, which I call F parallel here, and that component does all the work. So basically the work is magnitude of the parallel force times the distance, and well, the other component, which would be F perpendicular, which is the total force minus the parallel force, that component does no work. Basically this component provides a little bit of lift. Hopefully you're not going to pick up the pull toy or anything like that, but it doesn't contribute to the motion of the object. And I think that that should be intuitively reasonable, because if the object is moving horizontally, then a vertical force doesn't move the object left or right, and we're also saying here that we're not picking the object up. Okay, so that means that the work that is being done is equal to the magnitude of the parallel force times the magnitude of the distance, which is, okay, so first of all, that's still the parallel force, so work is force times distance. But we want to look at the original force, and if we're looking at the original force, we realize that the parallel force, of course, is just equal to the overall force times the cosine of the angle between the two forces, because we've got a right triangle here. Here's the right angle, and so we've got cosine theta is parallel force over total force. So that means total force, parallel force is total force times cosine theta, and so this would be the definition of work. And indeed, that's what it's going to be. However, we'd like to now also have a way to formulate the work in a vector definition that only refers to the vectors and at least not explicitly to the angle. So how do we do that? Well, first of all, let's notice that work equals force times distance times cosine theta. That is something that makes sense in any dimension. And that is because two vectors will define a plane, right? I mean, just think of two arrows just sitting there. No matter how many dimensions you surround them with, they're still sitting in a plane. And in a plane, we can measure angles. So that's nice. Unfortunately, there's no obvious way to obtain the angle from the component representation of the vectors, at least not yet. We will define one. And in most models, when we are looking at modeling with coordinate systems, of course, we will use components. And so that means we need a way to get this scalar product, norm of f times norm of d times cosine theta. We need to get that from the components somehow. And the key to the whole thing is that we remind ourselves of the law of cosines. The third side, the square of the third side of a triangle is a squared plus b squared. Well, that would be the law of Pythagoras, right? And the law of cosines is nothing else but a generalization of the law of Pythagoras, which says that c squared is a squared plus b squared minus 2ab cosine theta. And what we notice here is that this looks like a scalar product, right? This is a magnitude times the cosine of the angle between the two sides. So that is something that we will hopefully be able to use to derive a scalar product formula, as we're going to call this. So let's consider two vectors, a being a1, a2, and b being b1, b2. We put them in the plane because, as we've seen on the previous panel, technically two vectors are always sitting in a plane. We'll talk about higher dimensions on the next panel. And if we have the vector a here and the vector b here, and if we then take the vector b minus a, well, then we have a triangle. The angle between the two vectors, theta, is here, and so we can apply the law of cosines to this thing, right? And so we get that the square of the side opposite to the angle, which is b minus a norm squared, that by the law of cosines is equal to the norm of a squared plus the norm of b squared minus 2 times the norm of a times the norm of b times cosine theta. So here is exactly what we want to have. Sorry about the ugly highlighting, sometimes that happens. Here's exactly what we want to have, and this stuff here we can express in components. So that's what we'll do. So b minus a norm squared is a norm squared plus b norm squared minus 2 norm a norm b cosine theta. We solve for this part here, so we get 2 norm a norm b cosine theta is a squared plus b squared minus b minus a norm squared. And now we write those out in components. Well, the norm of a squared is a1 squared plus a2 squared. The norm of b squared is b1 squared plus b2 squared. And the norm of b minus a squared is b1 minus a1 squared minus b2 minus a2 squared. Of course, now we can multiply out the parentheses. So we keep the norm squared of a, we keep the norm squared of b. We multiply out these parentheses to get minus b1 squared plus 2a1 b1 minus a1 squared. So we've already also digested the negative sign. And we'll do the same thing with b2 minus a2 squared, which is minus b2 squared plus 2a2 b2 minus a2 squared, where again we first multiply it out and then pull this negative sign into the whole thing also. Okay, now we see something very nice, and that is that all the squared terms cancel, right? The a1 squared goes away with the minus a1 squared, a2 squared is also here, b1 squared is subtracted here, and b2 squared is subtracted here. So that means that the right-hand side is just 2a1b1 plus 2a2b2, and that means that the norm of a times the norm of b times cosine theta is just a1b1 plus a2b2. So we have a way to express this scalar product that we would like to have in terms of the components. And so what we're going to define is for vectors a equals a1 through an and b being b1 through bn, the scalar product or dot product is defined to be a dot b being a1 through an dot b1 through bn, which is the sum of the products of the ak, bk, or if you want to write it out, it's a1, b1 plus a2, b2 plus a3, b3, and so on, plus all the way to an, bn. Okay, so that's another formula that you definitely want to memorize because this scalar product will be a standard tool for us. And yeah, basically, I think on the next panel I'm saying, okay, first of all, again, in dimensions shouldn't be anything that scares us. In 2 dimensions, it would just be x product of the x components plus product of the y components. In 3 dimensions, if you take x, a, y, a, z, a dot x, b, y, b, z, b, it would be the product of the x components plus the product of the y components plus the product of the z components. And finally, a quick proposition. If a and b are 2 vectors in any dimension, and theta is the angle between them, well then a dot b, the dot product of those 2 vectors, is the magnitude of a times the magnitude of b times cosine theta. And I'm saying we don't have to prove anything here, and that is because this proof that we did in 2 dimensions was just done in 2 dimensions for convenience. If we had done the same thing in n dimensions, we would have had to keep track of n components, but we would have gotten the same result, and that is that magnitude of a times magnitude of b times the cosine of the angle between the 2 vectors is the sum of the products of the corresponding components. All right, let's take a look at what this can do for us. Well, the first example is, well, okay, come on, that's almost insulting. Compute the scalar product of the vectors a and b, where a is -1, 3, 2, and b is 4, 2, 5. What are you going to do? A dot b is -1, 3, 2 dot 4, 2, 5, so you get -4 plus 6 plus 10, right? So -1 times 4 plus 3 times 2 plus 2 times 5. And so -4 plus 6 plus 10 gives us 12. And that's it already, right? There's nothing for us to do here. We just use the definition and move on. It becomes a little bit more interesting when we talk about computing angles. And here again, even though I am fairly preachy about column vector notation, I'm using the bracket or angle notation here, and that's because I want to have the whole computation on one panel. So, if you need to compute the angle between the vectors, well, the cosine of the angle occurs in that proposition on the scalar product, right? A dot b is a norm times b norm times cosine theta, and of course, you can solve that for cosine theta. And so the first thing we need is a dot b, and we can compute that. That's 2, -1, 2 dot -3, 1, 6, which gives us -6 minus 1 plus 12, and that would be 5, okay? We need the magnitude of A, or the norm of A. I often say norm, I could also say magnitude or length. The magnitude of A is the magnitude of 2, -1, 2, which would be the square root of 4 plus 1 plus 4, right? Because we take the square root of the sum of the squares, so 4, 1, and 4 there. That's the square root of 9, which is 3. Magnitude of B is the magnitude of -3, 1, 6, which would be the square root of 9 plus 1 plus 36, exactly, and that's the square root of 46. We can't simplify that any, and that means that cosine theta, well, if you take the formula for the dot product expressed in terms of magnitudes and solve for cosine theta, you get that cosine theta is a dot b over the length of a times the length of b, which would mean for us that cosine theta is 5 over 3 times root 46, right? 5, 3, and root 46 here. That's approximately 0.2457. Of course, we're not interested in the cosine of theta, we're interested in theta. So theta is the arc cosine of 5 over 3 times root 46, which in radians is approximately 1.3225, and in degree measure it's 75.7746 degrees, and that's the computation. Now this is something that is fairly common. Every so often we will need to work with angles, but even more important than just the computation is this idea that yes, we can measure angles, because we will use this formula in various more abstract contexts than just this situation, and so this is just something that trains us in using this formula. All right, another definition. Two vectors a and b are called orthogonal or perpendicular. Perpendicular is the word that we are certainly more familiar with from our elementary classes. Orthogonal is something that people use in linear algebra as well as in other advanced classes, so we might as well remember it. Well, what does perpendicular mean? Perpendicular means they're at right angles, so orthogonal has to mean the same thing. And we say that that's the case if and only if the dot product is equal to 0. And of course, sure, that is clear, and that is because unless A is equal to 0 or B is equal to 0, so unless either one of those vectors has only components 0, A dot B equals 0 because of the formula magnitude of A times magnitude of B times cosine theta. A dot B equals 0 implies that the cosine of theta is equal to 0, and that means that theta is a right angle. Okay, so now let's look at some properties and at some applications. The properties are just algebraic, and so basically if you've got three vectors a, b, and c and a scalar s, well then the following hold. You have that a dot a is the magnitude of a squared. That should be pretty clear. You could get that directly from the formula, because a dot a is the sum of the squares of the components, and that's the square of the magnitude. Or you could also go with a magnitude times cosine theta, which is 0 when you take the angle between a and itself. A dot b is b dot a, so this is what mathematicians call that the product is commutative. A dot b plus c is a dot b plus a dot c, so you can multiply out parentheses. And if you've got a scalar times a dot b, then that's the same as if you take the scalar times the dot product, and that's the same as a dot scalar times b. And if you take a null vector, a vector that has components 0 all the way through, then null vector dot A is equal to 0 no matter what A is. Every so often we need the null vector. We already have seen that on the previous panel. Sometimes it's a pathological example because by definition the null vector is perpendicular to anything, for example. Well, so be it. I mean, that is just something that comes out of the definition and we live with it. These laws themselves, basically what they tell us is that algebra works as we're used to it, and that's good enough for calculus. If you're going into abstract linear algebra, if you're going into abstract algebra, all of a sudden you really have to pay attention to see which laws still hold. But for our purposes, for the most part, anything that we think ought to work does work here. As a proof, well, everything can be proved component-wise. I've sort of already talked or shadowboxed you through the first one. So we're going to prove part 2. That should be part 2 here, sorry. And so, well, A dot B is A1, A2 all the way through AN dot B1, B2 all the way through BN. And that's A1, B1 plus A2, B2 all the way through AN, BN. And of course, we know that for numbers, we can flip the factors. So this is B1, A1 plus B2, A2 plus all the way through BN, AN. And that's the dot product of the two column vectors, and that's B dot A. And that's it already. So this is something that is fairly simple to verify. If you have something like that assigned as a homework problem, for example, it is something that makes you more familiar and makes another symbolic connection for your brain with the component-wise formulation of the dot product, which is not bad to do. Okay, another definition: a force that moves an object on a straight distance d performs the work. Work equals dot product of the force with the distance. And that's because if we go back to the introduction, only the component that is parallel to the distance that you travel does all the work. And that means that the work is magnitude of the force times magnitude of the distance times cosine of theta, which is exactly what we have here. So that is, if you've got this object that you're moving with a force that is not parallel to the distance that the object travels, so it stands at an angle with the distance, then this parallel component is what does the work, and F parallel is just F times cosine theta. Hang on here. And we're back. Good. Sorry about that. The magnitude of the parallel force is, of course, just magnitude of the total force times cosine theta, because we've got this right triangle here that we've described already. Cosine of theta is magnitude of the parallel force over the total force, and that then means that the work that is done is magnitude of the parallel force times the magnitude of the distance, which is norm of F times norm of D times cosine theta. You can see here why I prefer to say norm instead of magnitude. I don't break my tongue so much. And this is what we now know to be the dot product of the force and the distance. Okay, so as an example, if we talk about my friend Dr. Absent-Minded, he also had a young daughter once. He still has a daughter. She's just grown up now. Say that young daughter is pulling a toy kitten for 100 meters along a sidewalk, and she pulls with a force of 3 newtons, and the angle between the string attached to the toy kitten and the horizontal ground is 60 degrees. How much work is the daughter doing? Well, that's exactly the picture that we have seen previously, and after all the visualizations and after the derivations and all the other stuff that we've done, all we really have to do to compute the work is to take the magnitude of the force, which is 3 newtons, times the distance, which is 100 meters, times the cosine of the angle in between, which is a cosine of 60 degrees, and work that out. So we get 300 times the cosine of 60 degrees is 1/2 root 3. The unit is Newton meters, and that gives us 150 root 3 Newton meters. All right, so you can see here that solving something like this is quite simple. And so again, you don't want your initial training in scalar products and things like that to deteriorate into just memorizing a formula and plugging things into a formula. You want to remember the ideas behind those formulas, because that's what ultimately will get us through modeling. Okay, what else do we have? Well, if we have a vector B and a vector A, and then there is an angle between those two vectors, then what we have seen for the force is we're interested in what happens when we project the vector B down on the vector A. And basically that projection, which is also called the projection of the vector B onto the vector A, is just so that it has length, magnitude of b times cosine theta, just like previously we had magnitude of f times cosine theta. But of course it also points in the direction of a, and so just as we've seen in the previous presentation, we're going to encode the direction with a unit vector in the direction of a, which is a over a norm. And well, that can be expressed a little bit simpler if we multiply top and bottom with a norm one more time, because then what we get is that if we multiply this thing here with a norm in numerator and denominator, we get the dot product of a and b on the top, and we get an a norm in the denominator, and we still have this unit vector here, and that leads to the following definition. If a and b are vectors, then the scalar projection of b onto a, which is also called the component of b in the direction of a, that is defined to be the component of b in the direction of a, and that's just a dot b over the norm of a, because it is just this component. The vector projection of b onto a is defined to be the projection of b onto a, and that's the whole thing that we've seen over here, a dot b divided by a norm times a over a norm. Okay, now you can easily make up a homework problem here. Compute the projection of the vector b equals, give yourself some numbers, onto the vector a, give yourself some numbers, and work it out. So I'm not going to show you how to do that because you know how to do this. The main idea in these formulas, even though a lot of what we're going to do in homework problems is simply that we assess, well, basically it's something you have to compute, and what it assesses is only whether you can plug numbers into the formula. What you want to keep with yourself, as I've said all along, is you have to keep with yourself the ideas behind those things, because that's what we're going to use later on in the course. We're finishing with something very quick, and that is, just as there is a lot of different notation for vectors, there is also different notation for scalar products. There are different notations for scalar products, namely the scalar product a dot b is also denoted ab without the dot, and it's also denoted left angle a comma b right angle. That is also called the bracket notation in physics. And yeah, that's already it. So again, the quick reminder, when you're running into different notations for these kinds of things, don't be in any way taken aback or so. It's still the same scalar product, it's still the same physics, it's the same mathematics. You just need to read it the right way. Alright, next up is the vector product. I'll see you then.